So
the
when you talk
future
about
bar.
U2 and UN, so I understand that the length of the vector is changing, the length of the complex number. I'm just a little bit confused about the U1, just because you drew there the two-dimensional representation, and I'm also not sure what's the difference between US special unitary. Is that in special unitary the determinant is strictly 1, as if in unitary it could be plus or minus 1? Is that the main difference?
No, in unitary, when you look at this, I won't go back, but well, I could go a little bit back. We found it that it was up to a phase. So, let's see, why did we do this? Someplace, looking at the determinant, determinant is a complex number because unitary matrix is a complex matrix, right? And we found that the determinant of U has a unit phase, e to the I theta, but it could be any phase. So what you can do is you can fix that phase to be exactly 1. So it's more general. When we looked at the rotation, the phase could be plus or minus 1. There's a difference between rotation group or orthogonal group ON and special orthogonal group was that special orthogonal group had determinant equals 1. There was a consequence of being able to move infinitesimally close to unity. And special orthogonal group in general, it could also have -1, which is very far away because you have to turn by 180 degrees to point the opposite way. Definitely not an infinitesimal transformation. When you go to unitary groups, then the statement is, not as dramatic, but it just says that unitary matrix can have any phase, and I can always construct from that matrix a special unitary group where I divide the determinant by this phase and guarantee that it has unit volume. So that's the difference between unitary and special unitary. Now, that kind of more formally means that whenever you have a unitary group, you can write it as a product of two groups. U1, it's one complex number, or in the drawing in a real plane, two real numbers. So that was U1. So the phase itself is U1. And then you can always say that unitary group is U1, which is this overall phase, times SUN, which is what's left when you remove it. And that's a special unitary group.
So the U1 basically is just giving you a phase.
So yeah, so it's 1 by 1 matrix in
so
complex number, or 2 by 2 in real numbers.
Right. So it's just a number. So if I'm looking at the magnitude of the number, it's Levitz invariant because the real part of the phase is always the same length.
Yeah, the real part is, so we got the UN by generalizing that U1, that complex phase.
So only like higher dimension 2 and above, I'm actually having some kind of a rotation, as if like one dimensional.
Well, here you have a rotation, which is, you see it in the Gauss representation, or actually Wessel's diagram, another Dane, I think. But if you represent complex number as two real numbers in the plane, then this theta is the angle of rotation in that plane. But as far as complex numbers are concerned, this is just a number, one complex number. Now for the other dimension, you'll have more handles to rotate. So SUN will actually have n squared minus 1 possible rotations hidden inside of it when we count its dimensionality.
Okay, so it's always 1 minus the dimension. The dimension minus 1.
And well, for the number of different rotations, different parameters, it's actually n squared. So, you know, un is a matrix of n times n complex numbers, so n square complex numbers. So you would think it's parameterized by n squared things, but then it has this strong condition that its Hermitian conjugate is its inverse. And that actually reduces the number of parameters, not to 2n squared, but just n squared. So the number of parameters of unitary group, and then we'll do this again, counted more carefully, but for unitary group, I have to specify n squared real numbers. And for special unitary, it's n squared minus 1 real numbers to describe a rotation of a complex vector in n dimensions.
Okay, thank you.
You're welcome. Thanks for asking.